As we accelerate toward the 21st century, the United States aerospace industry is challenging the world with the X-33 and the reusable launch vehicle. Only the lowest cost, most robust systems will survive the competition. One rocket propulsion system offers the right combination of performance and cost: the Aerospike engine. Its unique shape, highly integrated with the vehicle, and simple gas generator cycle enables the highest performance, lowest cost vehicle to be developed. The Aerospike is a mature engine concept with over $500 million invested to date by NASA and Rocketdyne. Its performance and operation have been verified by over 73 engine hot fire tests and 4,000 seconds of operation. In the early 70s, the Aerospike was a leading candidate for the Space Shuttle main engine. Starting in the late 1960s, Rocketdyne and NASA began developing the Aerospike engine. Testing was performed at all levels. The thrust cell shown here is a key component of the engine, where the propellants are mixed and ignited to produce thrust. Each cell develops a fraction of the total engine thrust. This allows the engine to be developed at a small size, thus lowering risk and cost. Multiple thrusters are then clustered on the Aerospike nozzle to create the required thrust level. The Aerospike is similar to other rocket engines, except that it has a very high efficiency nozzle. The nozzle is a truncated spike which directs the flow of high-pressure gases coming from the thrust cells. The gases expand against the surface of the nozzle to produce thrust, then continue to expand to enclose a subsonic, recirculating flow field at the base. Pressure from this flow field acts upon the base and produces additional thrust. Turbine exhaust gases are also discharged to the base to add thrust. These flows combine to produce very high nozzle efficiency, a major advantage of the Aerospike. Another major feature is altitude compensation. This is provided by the outer free jet boundary of the primary flow. At sea level conditions, the boundary is compressed, increasing pressure on the nozzle wall and base. As altitude increases, the boundary expands, keeping nozzle performance near the theoretical maximum for each altitude. Finally, the Aerospike's design also provides size and weight savings when compared to conventional Bell engines. Testing of linear Aerospike engines was initiated in September of 1971. 8 ignition and transient tests were conducted to develop a reliable start envelope. 25 tests were conducted with a combustion wave ignition system, which consisted of a central premixer, which initiated a detonation wave for simultaneous ignition of all thruster elements. The first linear engine used J2S turbomachinery and related hardware, had 20 thrust cells and produced 250,000 pounds of thrust. A total of 44 tests and 3,114 seconds of main stage operation was achieved during the test program, with one test running for 592 seconds. The test successfully mapped the engine's operational range, including chamber pressures from 680 to 1,250 psia and mixture ratios from 3.2 to 5.6. The second linear engine initiated testing in 1972. It also used J2S turbomachinery and related hardware, but had 10 thrust cells and produced 125,000 pounds of thrust. Nearly 30 tests and 1,000 seconds of operation were accumulated on this engine, including dynamic hinging of plus or minus 16 degrees and an assessment of thrust vector control using differential throttling. The Aerospike is the right engine for the 21st century. No other engine has the unique combination of very high performance and simple gas generator cycle as does the Aerospike. It allows the smallest, least expensive vehicle to be developed. With over $500 million invested to date and thousands of seconds of engine hot fire tests, the Aerospike is ready to become the rocket propulsion system for the next century.